Right now, Earth is spinning at over 1,000 miles per hour. It orbits the Sun at 67,000 miles per hour. The Sun itself circles the Milky Way at 500,000 miles per hour. And the Milky Way, a disk of 400 billion stars, rotates once every 230 million years. Everywhere scientists look, from atoms to accretion disks to galaxies spanning 100,000 light years, the universe is spinning. But here is the strange part. Nothing gave it permission to spin. No engine drives it, no hand set it turning. The reason everything rotates traces back to a single quiet law of physics, and a truth so simple it almost feels like a trick. Gravity does not create spin. It reveals spin that was already there. If you enjoy mind-expanding science journeys, do me a small favour and hit the like button. And if you are new here, subscribe so you never miss a story. Now, let's begin. Stand outside tonight and look up. The sky appears calm. Stars hang motionless. Constellations seem frozen in place. Nothing appears to be moving. But that stillness is the greatest illusion in nature. Everything you see is spinning. Everything you cannot see is spinning. Every object in the cosmos, from the smallest grain of interstellar dust to the largest structure ever observed, carries some amount of rotational motion. The universe is not a still photograph. It is a churning, rotating, spiraling machine, and the deeper you look, the more relentless that rotation becomes. The scale of this phenomenon is so vast, so total, so unavoidable, that it demands an explanation, and that explanation, when it finally arrives, will change how you see the cosmos forever. Start with the ground beneath your feet. Earth rotates on its axis once every 23 hours and 56 minutes. At the equator, the surface moves at roughly 1,037 miles per hour. You do not feel this speed because the atmosphere, the oceans, and the ground all move together, but the rotation is real, and its consequences are everywhere. It defines day and night. It drives atmospheric circulation patterns and bends ocean currents into enormous gyres. It shapes the Coriolis effect that twists hurricanes into spirals and deflects winds across entire continents. Earth's liquid iron core, churning within the spinning planet, generates the magnetic field that shields life from deadly solar radiation. Without rotation, that magnetic dynamo would cease. Without the magnetic field, the solar wind would strip away the atmosphere. Rotation does not just happen to Earth, it protects it. The planet you are standing on has been spinning for 4.5 billion years without a single pause, and it was spinning even faster in the beginning. When Earth first formed from colliding debris in the young solar system, it completed a full rotation in roughly 6 hours. Imagine a world where sunrise to sunrise lasted less time than a modern work shift. The sky would have wheeled overhead at dizzying speed. Tidal interactions with the moon have gradually slowed Earth's spin over billions of years, transferring rotational energy from the planet to the moon's orbit, which is why the moon drifts roughly 3.8 centimeters farther from Earth every year. The days have been getting longer ever since. Geological records preserved in ancient tidal sediments and fossilized coral growth rings confirm this slowdown. Roughly 370 million years ago, during the Devonian period, a year contained about 400 days, each lasting only about 22 hours. The dinosaurs lived through slightly shorter days than we do. Earth is slowly losing its spin, but even after 4.5 billion years of continuous gravitational braking, it still turns at over 1,000 miles per hour. That original rotation has been remarkably durable, a stubborn remnant of the forces that built the planet in the first place. But Earth is not spinning alone. The moon orbits our planet once every 27.3 days. That orbit is itself a form of angular momentum in action. The moon does not sit still beside us. It traces a smooth elliptical path through space, held in its orbit by Earth's gravity, completing circle after circle in an endless loop. And here is something most people never consider. The moon also rotates on its own axis. It turns exactly once for every orbit it completes, which is why we always see the same face. That locked rotation is not coincidence. It is the result of billions of years of gravitational interaction, tidal forces gradually synchronizing the moon's spin period with its orbital period until they matched perfectly. Scientists call this tidal locking, and it happens throughout the solar system. Many moons of Jupiter and Saturn are tidally locked to their parent planets. Even Pluto and its large moon Charon are mutually locked, forever facing each other as they spin through the outer solar system. Tidal locking is itself a consequence of rotation. It happens because rotation existed first, and gravity slowly reshaped it over time. Now step outward. Earth orbits the Sun at roughly 67,000 miles per hour. That velocity sounds extreme, but it barely registers on cosmic scales. Every planet in the solar system orbits the Sun. Mercury races around in just 88 days. Venus takes 225 days. Mars needs 687 days to complete one circuit. Jupiter takes nearly 12 years. Saturn takes 29 years. Distant Neptune, orbiting almost 3 billion miles from the Sun, requires 165 years to finish a single lap. Each planet traces its own elliptical path, and each of those paths carries angular momentum, a quantity so important to the universe that violating its conservation would break physics itself. But the planets do more than orbit. They also rotate on their own axes. Jupiter, the largest planet in the solar system, is a monster of rotation. Despite being over 11 times Earth's diameter, it completes a full spin in just under 10 hours. That furious rotation drives wind bands thousands of miles wide and sustains storms like the Great Red Spot, a hurricane-like vortex larger than Earth that has been raging for centuries. Jupiter spins so fast that its equator bulges outward, making the planet visibly wider than it is tall. Saturn rotates in roughly 10.5 hours and shows a similar equatorial bulge. Earth completes one rotation every 24 hours. Mars turns at roughly the same rate. Even slow-spinning Venus rotates, though it does so backward compared to most other planets, taking 243 Earth days to complete a single turn, while orbiting the Sun in only 225 days. Venus's day is longer than its year. That bizarre retrograde spin likely resulted from a catastrophic collision early in the solar system's history, an impact so violent it reversed the planet's rotation entirely. Uranus presents another oddity. It is tilted 98 degrees on its side, essentially rolling along its orbit like a ball rather than spinning upright like a top. Again, a massive ancient impact is the most likely explanation. These exceptions are important. They show that while rotation is universal, its direction and orientation are not predetermined. Each object's spin is shaped by its unique history of formation and collision. The Sun itself is not exempt from this cosmic rule. Our star rotates roughly once every 25 days at its equator. Because the Sun is not a solid body but an enormous sphere of ionized plasma, its rotation rate varies with latitude. The equator spins faster than the middle latitudes, and the poles take roughly 35 days per rotation. This differential rotation is not a minor detail. It is the engine behind the Sun's entire magnetic personality. The uneven spinning stretches, wraps and tangles magnetic field lines beneath the surface, building tension over years until the stressed fields burst through the photosphere as dark sunspots and erupt as solar flares, releasing energy equivalent to billions of nuclear weapons detonating simultaneously. Coronal mass ejections, vast bubbles of magnetized plasma hurled into space at millions of miles per hour, are another direct consequence of this magnetically tortured rotation. The 11-year solar cycle, during which sunspot activity rises to a frenzy and then subsides to quiet, is driven entirely by the interplay between the Sun's differential rotation and its internal magnetic field. Every roughly 11 years, the accumulated twisting becomes so extreme that the Sun's magnetic poles flip, north becoming south and south becoming north, before the cycle begins again. Take the rotation away, and the Sun becomes a magnetically dead star, featureless and serene, incapable of producing the dynamic space weather that shapes conditions throughout the entire solar system. Rotation does not just happen to stars. It fundamentally shapes their behavior, their magnetic fields, and their influence on surrounding planets across their entire lifetimes. This is where the story begins to feel unsettling. If you look at the solar system from above the Sun's North Pole, nearly everything orbits in the same direction. All 8 major planets revolve counterclockwise. Most of them also rotate counterclockwise on their axes. The Sun itself rotates counterclockwise. Even most of the large moons orbit their parent planets counterclockwise. The entire system shares a common rotational direction, as though it were choreographed by a single architect. And the solar system is flat. All the major planets orbit within a narrow plane, tilted no more than a few degrees from one another. The system is not a sphere of randomly scattered orbits. It is a disk, thin and organized, with the sun at the center and everything revolving in the same sense around it. That flatness is not a coincidence. It is a clue, perhaps the most important clue in the entire story of cosmic rotation. The solar system is flat because it formed from a flat structure, a vast rotating disk of gas and dust that surrounded the young sun approximately 4.5 billion years ago. Scientists call this a protoplanetary disk, and its existence has been confirmed beyond any doubt by direct observation around other young stars throughout the galaxy. Telescopes like the Atacama Large Millimeter Array in Chile have photographed hundreds of these disks in vivid detail, revealing thin rings and gaps of dust and gas encircling newborn stars, glowing faintly in infrared and sub-millimeter light. Some of these disks show concentric gaps where young planets are actively forming, carving channels through the dust as they grow. Every one of those observed disks is rotating. Every one of them is flat. The pattern repeats across the galaxy like a universal template stamped onto every new star system that forms. Why does that matter? Because those disks did not appear by magic. They formed through a physical process that connects directly to the mystery of universal spin. A protoplanetary disk is what happens when a massive cloud of gas collapses under its own gravity, but cannot fall straight inward because it carries a tiny amount of sideways motion. That sideways motion, that faint residual drift, becomes rotation, and as the cloud shrinks, that rotation intensifies dramatically. The disk is the physical consequence of rotation being preserved and amplified during gravitational collapse. We will return to the precise mechanism later. For now, what matters is the observation itself. Rotating disks appear everywhere stars are born, and disks mean rotation was there from the very start. Stars themselves are born spinning. When a dense core inside a molecular cloud collapses to form a new star, it inherits the rotational motion of the material that created it. Young stars called T-Tauri stars spin rapidly, sometimes completing a full rotation in just a few days. These are stellar infants, still surrounded by the remnants of their birth disks, still accreting material from their surroundings. As they age and interact with their remaining disks, magnetic braking and powerful stellar winds gradually slow them down. But the initial spin is always there, imprinted at birth, carried forward from the parent cloud. No star is born motionless. Every star enters the universe already turning. Now look beyond individual stars at the structures that surround them when matter falls toward extremely dense objects. Accretion disks appear wherever infalling material cannot shed its angular momentum quickly enough. Around young stars, these disks are the protoplanetary nurseries where planets are born. But accretion disks also appear in far more extreme and violent environments. When a star in a close binary system overflows its gravitational boundary and begins transferring mass to a companion white dwarf, neutron star or black hole, the infalling material does not plunge straight in. It swirls. It forms a disk of superheated gas spiraling inward, heating up as gravitational energy converts to thermal radiation. These disks can reach temperatures of millions of degrees, glowing in X-rays and ultraviolet light so intense that they outshine entire star systems. And their existence depends entirely on rotation. Without angular momentum, the material would fall straight to the surface or through the event horizon. The disk exists because the gas is spinning too fast to plunge directly inward. It spirals gradually, shedding angular momentum through friction, turbulence, and magnetic interactions, converting gravitational potential energy into radiation at extraordinary efficiency. These accretion disks are not rare or exotic. They appear around white dwarfs in cataclysmic variable star systems, periodically erupting in spectacular outbursts called novae when accumulated hydrogen ignites in thermonuclear flashes on the white dwarf surface. They surround neutron stars in X-ray binary systems, where the disk becomes so intensely hot, reaching tens of millions of degrees, that it radiates primarily in X-rays detectable only by orbiting telescopes above Earth's atmosphere. And most dramatically, accretion disks encircle the supermassive black holes at the centers of galaxies, forming the blazing cores of active galactic nuclei and quasars that can outshine the entire surrounding galaxy of hundreds of billions of stars by factors of hundreds or even thousands. The supermassive black hole at the center of the galaxy M87, famously imaged by the Event Horizon Telescope in 2019, is surrounded by a glowing asymmetric ring of accreting material, a disk of gas spiraling inward at a significant fraction of the speed of light, heated to billions of degrees by compression and friction. That image, the first direct photograph of a black hole's shadow, is essentially a photograph of rotation in its most extreme form. The bright ring exists because matter is orbiting so fast, so close to the event horizon, that it glows with the energy of its own motion. Without rotation, there would be no ring, no disk, no image, just a silent, invisible void swallowing matter in darkness. In every case, from city-sized white dwarfs to supermassive black holes containing billions of solar masses, the underlying physics is identical. Matter falls inward. Angular momentum prevents a direct plunge. A spinning disk forms. Gravitational energy converts to radiation. Rotation is the engine behind some of the most luminous and violently energetic phenomena in the known universe. Scale up even further and the rotation only becomes more dramatic. The Milky Way itself is a rotating disk of stars, gas, dust, and dark matter. The Sun and everything in our solar system orbit the galactic center at approximately 515,000 miles per hour. That seems incomprehensibly fast, yet at this speed, one complete revolution around the galaxy takes roughly 230 million years. Scientists sometimes call this period a galactic year. Since the Sun formed about 4.5 billion years ago, our solar system has completed approximately 20 orbits around the galaxy. The dinosaurs last walked Earth less than 1 galactic year ago. In cosmic terms, the galaxy has barely turned since they vanished. But the Milky Way is not the only spinning galaxy. Virtually every disk galaxy astronomers have observed rotates. Andromeda rotates. The Triangulum galaxy rotates. Distant spirals billions of light years away show the unmistakable signatures of rotation in their spectral lines. One side of the galaxy is blue shifted, its light compressed as it moves toward us. The other side is red shifted, its light stretched as it recedes. This spectral splitting proves the disk is turning. Even elliptical galaxies, which lack organized spiral structure, show internal rotation within their stellar populations when examined with modern integral field spectrographs. Galaxies are not static collections of stars suspended in space. They are dynamic rotating systems, and their rotation plays a central role in shaping their spiral arms, their magnetic fields, their chemical evolution, and their ultimate fates. The rotation of galaxies produced one of the great puzzles of 20th century astronomy, a puzzle that rewrote our understanding of what the universe is made of. When scientists first measured how fast stars orbited within spiral galaxies, they found something deeply disturbing. Stars at the outer edges move far too quickly. In our own solar system, the pattern is clear and predictable. Mercury, closest to the Sun, orbits at roughly 107,000 miles per hour. Earth, farther out, moves at 67,000. Distant Neptune crawls along at just 12,000 miles per hour. Orbital speed drops with distance because the Sun's gravitational pull weakens with range. Galaxies should work the same way. Most of the luminous mass concentrates near the galactic center, so stars in the outskirts should orbit slowly, weakly held by diminished gravity at the galaxy's periphery. Instead, they raced along at speeds that should have flung them straight into intergalactic space. The galaxy's rotation curve, the graph plotting orbital speed against distance from the center, stayed stubbornly flat far out into the disk where it should have dropped sharply. Astronomer Vera Rubin and her colleague Kent Ford documented this flat rotation curve across galaxy after galaxy in the 1970s and 1980s, building an overwhelming case that something was deeply wrong with the standard picture. The outer galaxy was spinning too fast for the visible matter to hold it together. Either the laws of gravity were broken, or something massive and invisible was providing the extra gravitational pull needed to keep those outer stars in orbit. That something turned out to be dark matter, an invisible form of mass that interacts with ordinary matter only through gravity and outweighs visible matter by roughly 5 to 1. Enormous dark matter halos surrounding every galaxy provide the gravitational scaffolding that keeps the outer stars bound. The rotation of galaxies did not just reveal how galaxies move. It exposed the existence of an entirely invisible component of the universe that constitutes most of the mass in the cosmos. Rotation was the diagnostic tool. Dark matter was the hidden patient it uncovered. Now push even further beyond individual galaxies into the grandest structures in the cosmos. Galaxies are not scattered randomly through space. They concentrate along vast filaments of dark matter and gas that stretch across hundreds of millions of light years, forming a web-like architecture called the cosmic web. Dense nodes at the intersections of filaments host galaxy clusters containing thousands of galaxies. Between the filaments lie enormous voids, regions of space nearly empty of matter. This cosmic web is the largest known organizational pattern in the universe. For decades, scientists assumed these filaments were essentially static scaffolding, highways of matter connecting galaxy clusters but not themselves carrying significant rotational motion. That assumption collapsed. In 2021, a team led by Peng Wang and Noam Libeskind published the first statistical evidence that cosmic filaments rotate. Galaxies on opposite sides of a filament's central spine were found moving in opposite directions, one side approaching and the other receding, exactly the signature you would expect if the entire filament was spinning around its long axis like a slow-motion cosmic tornado. The discovery was unexpected because no widely accepted theoretical model had predicted that structures this large, tens of millions of light-years long and composed of hundreds of galaxies, would exhibit coherent rotational motion. Then in December of 2025, an international team led by the University of Oxford reported something even more striking, a discovery that pushes the story of cosmic spin to scales that had seemed impossible. Using data from a deep radio survey conducted with the Meerkat telescope in South Africa, combined with optical observations from the Dark Energy Spectroscopic Instrument and the Sloan Digital Sky Survey, they identified one of the largest rotating structures ever observed, a razor-thin chain of 14 hydrogen-rich galaxies, stretching 5.5 million light-years, sat embedded within a much larger cosmic filament, approximately 50 million light-years long, and located about 140 million light-years from Earth. The galaxies within this chain were not just orbiting randomly. They were spinning in alignment with each other and with the filament itself. The researchers estimated a rotation speed of approximately 110 kilometers per second and found that the coordinated motion was far stronger than random chance could explain. The lead researchers compared the motion to a teacup ride at a theme park, where each cup spins on its own axis while the entire platform rotates as a whole. Except in this case, the ride is 50 million light-years wide. This discovery does not just add another spinning object to the cosmic list. It challenges existing models of how rotation originates at the largest scales. If individual galaxies acquire their spin through local gravitational interactions during formation, how does an entire filament, spanning 50 million light-years, develop coordinated rotational motion? What physical mechanism transfers angular momentum across such enormous distances? The standard framework explaining galaxy spin acquisition, called tidal torque theory, describes how gravitational tugs from neighboring structures during the early phases of collapse impart angular momentum to forming galaxies. But whether that same framework can scale up to explain filament-wide rotation remains an open and actively debated question. The 2025 result is a confirmed observation, published in the monthly notices of the Royal Astronomical Society. The full theoretical explanation has not yet caught up. The sheer range of scales involved is staggering. Rotation appears in systems spanning more than 20 orders of magnitude in size. A spinning neutron star, the ultra-dense collapsed remnant of a massive star, measures roughly 20 kilometers across, smaller than most cities on Earth, yet it can rotate hundreds of times per second. A protoplanetary disk around a young star might stretch a few hundred astronomical units, roughly 30 billion kilometers from edge to edge. A spiral galaxy spans 100,000 light-years or more. A rotating cosmic filament extends 50 million light-years. If you could line up every type of spinning object in the universe from smallest to largest, the progression would stretch across a factor of more than 10 trillion in size, and at every single step along that ladder, you would find rotation. From objects smaller than Manhattan to structures that dwarf entire galaxy clusters, rotation is present. It is not occasional. It is not limited to special environments or rare conditions. It is universal, persistent, and relentless. And the directions of rotation are beautifully independent. Galaxies do not all spin the same way. The Milky Way rotates in one direction, but a neighboring galaxy may spin in the complete opposite sense. There is no cosmic gear system linking one galaxy's rotation to the next. Each galaxy's spin axis and rotational direction are determined by the specific gravitational environment and initial conditions that shaped its formation. Some galaxies within clusters spin clockwise as seen from a given vantage point, while their neighbours spin counterclockwise. Some galaxies even show signs of having had their spin reversed or dramatically reoriented by major collisions with other galaxies. Rotation is universal in its presence, but anarchic in its direction. This combination of ubiquity and independence is itself a powerful clue. It tells us that rotation does not come from a single cosmic event or a single global cause. It arises from something more local, more fundamental, more inevitable. Here is what makes this observation so deeply strange. You can imagine, at least mathematically, a universe in which matter simply collapses straight inward, forming perfectly spherical blobs of stars and gas with no rotation at all. A perfectly symmetrical collapse, with every particle falling directly toward the center along a purely radial path, with no sideways motion of any kind, would produce no spin whatsoever. The result would be a static, featureless sphere, no disks, no orbits, no spiral arms, no weather patterns on spinning planets, no magnetic dynamos churning inside stellar cores to drive the flares and eruptions that shape entire solar systems, no accretion-powered jets screaming out of black holes at nearly the speed of light. A universe without rotation would be unrecognizably different from the one we inhabit. Stars would be magnetically inert. Planets would have no day or night. Galaxies would be shapeless blobs rather than elegant spirals. The structures that make the universe beautiful, complex, and capable of supporting life would simply not exist. It would be a cosmos of motionless spheres, dark and quiet and structurally dead. Instead, everywhere we look, matter has organized itself into spinning disks, orbiting systems, and rotating structures of breathtaking complexity. From the smallest stellar nurseries to the largest filaments in the cosmic web, rotation is not an accident or a quirk. It is the default outcome. And that outcome traces back to a single law of physics, a conservation principle so fundamental that it ranks alongside the conservation of energy as one of the bedrock rules governing reality. It is the conservation of angular momentum. And once you understand what it means and what it does when gravity collapses matter inward, the spinning universe stops being mysterious and starts feeling inevitable. But understanding that inevitability requires looking closely at what angular momentum actually is, how it behaves when clouds of gas shrink under their own weight, and why even the faintest trace of sideways motion in a collapsing system becomes impossible to ignore. What comes next reveals how gravity, the force that pulls everything inward, paradoxically creates the most spectacular rotational motion in the cosmos. Everything we have seen so far points toward a single question. Why does the universe spin? Not why does one particular planet spin or one particular galaxy rotate, but why does rotation appear at every scale, in every environment, across every structure astronomers have ever examined? We saw rotation in the orbits of planets and the spin of the sun. We saw it in the flat disks around young stars and in the swirling maelstroms surrounding black holes. We saw it in the spiral arms of galaxies and in enormous cosmic filaments stretching tens of millions of light years. Rotation is not something that happens to some objects under special conditions. It is the universal default. Anything that forms through gravitational collapse seems destined to spin. The answer to why this happens is not an event. It is not something that occurred once and set everything turning. It is a law, a rule built into the deepest architecture of physics itself. And to understand that law, you first need to understand a quantity that most people have heard of but very few truly grasp: Angular momentum. The name sounds technical and abstract. The concept behind it is among the most powerful in all of science, and once you understand it, every spinning object in the cosmos will make perfect sense. Start with something simpler, regular momentum. You already have an intuitive sense of what it means. A bowling ball rolling toward you carries more momentum than a tennis ball at the same speed because it has more mass. A bullet has less mass than a bowling ball but moves so fast that its momentum is devastating. Momentum is the combination of mass and velocity. Heavy things moving fast are hard to stop. This idea has been understood since Isaac Newton formalized it in the 1680s. Linear momentum, the momentum of objects moving in straight lines, is conserved. In any closed system where no outside force interferes, total momentum stays the same. You can transfer it, redistribute it, pass it from one object to another in a collision, but you cannot make it vanish from the system. It is one of the foundational rules of the physical universe. Angular momentum is the rotational cousin of linear momentum. It describes how much rotational motion a system carries and how hard that rotation would be to stop. But here is what surprises most people. You do not need to be visibly spinning to have angular momentum. Any object moving past a point, not directly toward it but off to one side, carries angular momentum relative to that point. This is the key insight that unlocks the entire mystery of cosmic rotation. Picture a billiard table. Place your fist on the felt and roll a ball directly at your knuckles. The ball hits your fist and stops. That ball had linear momentum but zero angular momentum relative to your fist because it was heading straight at the target. Now roll the ball again, but this time aim it slightly to the left of your fist. The ball slides past your hand without hitting it. Even though the ball is moving in a straight line across the table, it has angular momentum relative to your fist because it passes off-center. If you could somehow attach a string between your fist and the ball, pulling it inward, the ball would not fly straight into your hand. It would curve. It would spiral inward, moving faster as the string shortened. That curving, accelerating spiral is angular momentum being conserved as the distance shrinks. This off-center motion is the secret ingredient behind every spinning structure in the universe. A particle of gas drifting through a molecular cloud does not need to be orbiting anything. It does not need to be part of a spinning disk. It just needs to be moving in any direction that is not aimed perfectly at the cloud's center of gravity. And in a real cloud of gas containing trillions upon trillions of particles, all drifting in slightly different directions due to turbulence, thermal motion, and gravitational nudges from neighboring clouds, virtually none of those particles are heading directly toward the center. Almost every single one carries some angular momentum. The cloud is not spinning in any organized sense. It is a mess of random motions. But those random motions add up, and they almost never add up to exactly zero. Angular momentum depends on three things: the mass of the moving object, the speed at which it is moving, and the distance between the object and the axis around which you are measuring rotation. Increase any of these three, and the angular momentum increases. A heavier object moving at the same speed at the same distance carries more angular momentum. A faster object at the same distance carries more. And critically for our story, an object at a greater distance from the center carries more angular momentum, even if its speed stays the same. This last factor is what makes gravitational collapse so explosive. When matter falls inward and the distance to the center shrinks, something else must compensate to keep the total angular momentum unchanged. That something is speed. The rotation rate must increase. This is the conservation of angular momentum, and it is not a gentle suggestion or an approximate tendency. It is absolute. In any system where no external twisting force, what physicists call a torque, acts upon it, the total angular momentum remains exactly constant. Not approximately constant, not usually constant, not constant under ideal laboratory conditions, but wobbly in the real world. Exactly constant, down to the last measurable decimal place, everywhere in the universe, at all times. This law has been tested in laboratories on Earth, verified in the precise orbits of planets across centuries of astronomical observation, confirmed in the collapse of dying stars observed through telescopes millions of light years away, and written into the mathematical structure of quantum mechanics and general relativity alike. It has never once been violated. Not a single credible experiment or observation, in the history of physics has ever demonstrated a violation of angular momentum conservation. It is as fundamental and unbreakable as the conservation of energy, and for a deep mathematical reason. In 1918, the mathematician Emmy Noether proved that every conservation law in physics corresponds to a symmetry in the laws of nature. The conservation of energy reflects the fact that the laws of physics do not change over time. The conservation of linear momentum reflects the fact that the laws of physics are the same everywhere in space. And the conservation of angular momentum reflects the fact that the laws of physics do not depend on which direction you face. Space has no preferred orientation. You can turn any experiment to face north, south, east, or any angle in between, and the physics will work identically. That rotational symmetry of space itself is the reason angular momentum is conserved. It is not a rule imposed from outside the universe. It is a consequence of the universe's own geometric structure. You have seen this law in action even if you did not recognize it. A figure skater begins a spin with arms extended, rotating slowly. She pulls her arms inward, drawing mass closer to her axis of rotation. Her distance from the axis shrinks. To conserve angular momentum, her spin rate explodes. She goes from a leisurely turn to a blur so fast the human eye can barely track her. When she extends her arms again, she slows down. The total angular momentum never changed. It was merely redistributed between distance and speed. What the skater does deliberately, gravity does to collapsing clouds of gas on scales billions of times larger. The physics is identical, only the size changes. But before we watch gravity perform this trick, we need to confront an uncomfortable question. If angular momentum is conserved, it cannot be created from nothing. It must already exist before collapse begins. So where does the initial angular momentum of a collapsing cloud come from? If the primordial gas that filled the early universe were perfectly uniform and perfectly still, there would be no angular momentum to amplify. Collapse would produce spheres, not disks. Stars would not spin. Planets would not orbit. Nothing in the universe would rotate. Fortunately for us, and for every structure in the cosmos, the universe has never been perfectly still. Molecular clouds, the vast cold reservoirs of gas and dust from which stars are born, are turbulent places. They are among the most complex fluid systems in nature. They are stirred by shock waves from nearby supernova explosions, which send blast waves rippling through the interstellar medium at thousands of kilometers per second. They are compressed by the density waves of spiral arms as their host galaxies rotate. They are buffeted by intense stellar winds from massive nearby stars, pushed and pulled by ultraviolet radiation that heats and ionizes their surfaces, and threaded by magnetic fields that channel gas flows in complex, tangled patterns. The gas inside these clouds moves in every direction, sometimes fast, sometimes slow, sometimes slamming into neighboring streams and creating swirling eddies that cascade down to smaller and smaller scales. These motions are essentially random. No single direction dominates. No organized rotation pattern is evident when you look at the cloud as a whole. The cloud is not spinning in the way a wheel spins. It is churning, like a pot of water heated from below, riddled with convective currents that flow in every direction at once. But here is the critical insight. Random does not mean zero. Imagine flipping a coin 1,000 times. You would expect roughly 500 heads and 500 tails, but you almost never get exactly 500 of each. Sometimes you get 512 heads, sometimes 493. The deviations are small relative to the total, but they are real and they are unavoidable. This is a basic fact of statistics. Any finite collection of random events will show small imbalances. The imbalances are tiny compared to the total, but they are never exactly zero. The same principle applies to the random gas motions inside a molecular cloud. Trillions of particles are moving in every direction. Most of the angular momentum contributions cancel out. A particle drifting clockwise is offset by another particle drifting counterclockwise, but the cancellation is never perfect. There is always a tiny surplus, a small net angular momentum pointing in some particular direction. This residual spin is almost undetectable in the full-sized cloud. A molecular cloud stretching several light-years across might complete one full rotation every 10 million years. That is a rotational velocity so slow that the edge of the cloud moves at roughly the pace of a gentle walk. Compared to the violent internal turbulence, this net rotation is practically invisible. No telescope pointed at the cloud would register organized spinning. The cloud looks motionless, but it is not. It carries a tiny, almost negligible angular momentum, and that tiny amount is about to become the most important quantity in the entire system. Now gravity enters the story, and everything changes. A dense region within the molecular cloud, perhaps compressed by a passing shock wave, or pushed past its stability threshold by the slow accumulation of mass from surrounding gas, begins to collapse. The mutual gravitational attraction of the particles within this region pulls them inward. Material that was drifting lazily through space begins to accelerate toward the growing center of mass. The cloud fragment contracts. Its radius shrinks, and conservation of angular momentum tightens its grip like a physical law that has been waiting patiently for exactly this moment. The relationship is precise and merciless. Angular momentum equals mass times velocity times radius. If mass stays roughly constant during the collapse, an angular momentum must remain unchanged because no external torque is acting on the system, then velocity and radius are locked in an inverse relationship. When the radius decreases, the velocity must increase. Not by a little, not proportionally, by a factor that mirrors the square of the contraction. Halve the radius and the rotation rate quadruples. Shrink the radius by a factor of 10 and the rotation rate increases by a factor of 100. Shrink it by a factor of 1000 and the rotation rate soars by a factor of 1 million. The math is relentless and it does not negotiate. Real molecular cloud cores shrink by enormous factors during the process of star formation. A dense core might begin with a radius of roughly 10,000 astronomical units, which is about 1 trillion kilometers. The star that eventually forms from it has a radius of roughly 1 million kilometers. That is a contraction by a factor of approximately 1 million. The conservation law demands that the rotation rate increase by an enormous factor. A barely perceptible crawl becomes a ferocious spin. The gentle once per 10 million years rotation of the parent cloud transforms into a once per few days rotation of the newborn star. This is the critical revelation. Gravity does not create rotation. It has no mechanism to produce angular momentum from nothing. What gravity does is compress matter, reducing the radius of the system. Conservation of angular momentum then forces the rotation rate to increase. Gravity is the amplifier. The initial angular momentum, however minuscule, was always there. Gravity simply concentrated it into a smaller volume, making it impossible to ignore. Think of it like a river narrowing into a gorge. The river upstream might be broad and sluggish, its current barely noticeable, but as the banks close in and the channel narrows, the same volume of water is forced through a smaller opening. The current accelerates. The water rushes and churns and foams. No new water was added. No pump was activated. The narrowing channel simply concentrated the existing flow. Gravity does the same thing to angular momentum. The collapsing cloud is the narrowing gorge, the gas is the water, and the resulting spin is the roaring current that emerges from a seemingly placid source. Now comes the question that connects angular momentum to every flat structure in the universe. When a cloud collapses with angular momentum, why does it form a disk instead of some other shape? Why not a spinning sphere? Why not an elongated cigar rotating end over end? Why not an irregular blob? The answer reveals one of the most elegant and satisfying pieces of physics in all of astrophysics, and it has to do with a fundamental asymmetry that rotation creates in the collapsing system. Consider the collapsing cloud from two different perspectives. First, look at it from the side, viewing along the equatorial plane, the plane perpendicular to the rotation axis. Gas in this equatorial zone is orbiting the center of mass. It has substantial sideways velocity. As it tries to fall inward under gravity, it reaches a radius where the inward pull of gravitational attraction is exactly balanced by the tendency of the orbiting material to continue in a straight line, the effect we describe as centrifugal force in a rotating reference frame. At this equilibrium radius, the gas settles into a stable circular orbit. It cannot fall any farther inward because its angular momentum forbids it. Shedding that angular momentum requires some interaction, some friction or magnetic stress or turbulent collision, to transfer the rotational energy elsewhere. Until that happens, the gas is trapped, orbiting the center, unable to reach the center no matter how strong gravity pulls. Now look at the same cloud from above, viewing along the rotation axis. Gas approaching the center of mass from directly above or below the disk plane has a completely different experience. This material is falling parallel to the rotation axis. It has no sideways velocity relative to the center in the plane of rotation. It carries no angular momentum in the direction that would resist infall. There is no centrifugal barrier in its path. Nothing prevents it from plunging straight toward the midplane. This material can fall freely, unimpeded by rotation, accelerating under gravity until it crashes into the equatorial region, dissipates its kinetic energy through violent collisions and shock waves, and settles into the thin, dense layer of material accumulating in the orbital plane. The result is strikingly asymmetric. Collapse along the rotation axis proceeds freely and rapidly. Collapse in the equatorial plane is resisted by angular momentum and stalls at the equilibrium radius. The three-dimensional cloud squashes into a two-dimensional disk. Material piles up in the plane of rotation while the polar directions empty out. The disk grows thinner and denser over time as more material rains down from above and below, while the radial extent stays locked by angular momentum. This is why every protoplanetary disk is flat. This is why the solar system's planets orbit in a thin plane. This is why spiral galaxies look like cosmic frisbees rather than fuzzy spheres. This is why accretion disks around compact objects are razor-thin rings of superheated gas rather than spherical clouds of infalling material. The flatness is not a coincidence. It is not a design choice. It is the inevitable, mathematically unavoidable consequence of gravitational collapse acting on matter that carries angular momentum. Any system that collapses with even the tiniest net rotation will produce a flat disk. The universe makes disks the same way a potter's wheel makes flat plates. The spinning shapes the structure, but there is a problem lurking inside this beautiful picture, and it is severe enough that it threatened to break the entire theory of star formation when scientists first recognized it in the mid-20th century. The problem is this: molecular clouds carry far too much angular momentum. If all of a collapsing cloud's angular momentum ended up in the final star, that star would be spinning so fast it would rip itself apart. The specific angular momentum of a typical molecular cloud core, the angular momentum per unit mass, is roughly 1 million times greater than the specific angular momentum of the star that forms from it. Somewhere during the collapse, 99.999% of the angular momentum must be removed from the material that becomes the star. If it is not removed, the star cannot form. It would spin itself to pieces long before reaching stellar density. This is called the angular momentum problem of star formation, and it is one of the most important unsolved puzzles in astrophysics for the better part of half a century. Solving it occupied generations of researchers and required advances in both theoretical modeling and observational technology. The solution, confirmed by observations over the past 3 decades through infrared telescopes, radio interferometers, and space-based observatories, involves multiple mechanisms working together in a coordinated assault to drain angular momentum away from the collapsing inner regions and transport it outward. Magnetic fields play a central and often underappreciated role. Molecular clouds are threaded by weak but pervasive magnetic fields, generated and sustained by the motions of charged particles within the interstellar medium. As the cloud collapses, these field lines are dragged inward with the infalling gas, because the partially ionized gas is coupled to the magnetic field. But the field lines also connect the collapsing core to the slower-moving outer envelope of the cloud, material that is barely participating in the collapse. This magnetic linkage acts like a brake, an invisible tether connecting the rapidly spinning inner core to the sluggish outer material. The inner material, trying to spin faster as it contracts, is connected by magnetic tension to the outer material that is practically stationary. The magnetic field transfers angular momentum from the fast-spinning interior to the slow exterior, draining rotational energy from the collapsing core and depositing it in the surrounding envelope. Scientists call this process magnetic braking, and it is one of the primary mechanisms that allow stars to form without spinning themselves to destruction. Without magnetic braking, most collapsing clouds would reach rotational velocities so extreme that they would fragment into multiple pieces before ever forming a coherent star. The protoplanetary disk itself is another critical repository for the excess. As the inner core sheds angular momentum, that momentum does not vanish from the universe. It cannot, because the conservation law forbids it. Instead, it flows outward into the growing disk. The disk absorbs the excess and stores it in the orbital motion of its gas and dust particles, each one circling the central protostar at velocities determined by its distance. This is why protoplanetary disks extend so far from their central stars, sometimes reaching hundreds of astronomical units, hundreds of times the Earth-to-Sun distance. The disk is not leftover debris. It is not wasted material that failed to become part of the star. It is the angular momentum bank account of the entire system. The star deposits its excess rotational energy into the disk, and the disk carries that energy outward to larger and larger radii, where it can be accommodated without threatening the star's structural integrity. And then there are the jets, some of the most spectacular structures in stellar astronomy. Young stars frequently launch powerful bipolar outflows, tightly collimated beams of ionized gas accelerated to speeds of hundreds of kilometers per second and shot outward along the rotation axis, perpendicular to the disk plane. These jets can extend for light years, punching through the surrounding molecular cloud and lighting up shock-heated gas at their tips in glowing structures called Herbig-Haro objects. But their visual spectacle is secondary to their physical function. Every particle ejected in a jet removes a portion of the system's rotational burden. The jets carry angular momentum away from the star disk system entirely, dumping it into interstellar space, where it dissipates harmlessly among the vast emptiness between stars. The jets are angular momentum exhaust pipes, venting excess spin that the disk alone cannot absorb quickly enough. Together, magnetic braking, disk formation, and jet launching solve the angular momentum problem. The star gets the mass, the disk and the jets get the angular momentum. This division is not optional. It is required by the conservation law. The angular momentum must go somewhere. It cannot be destroyed, so it is transferred, redistributed, and exported, leaving the star free to contract to stellar density without tearing itself apart. And here is the consequence that connects everything back to the question of why the universe is full of planets and moons and rings and orbiting systems. The protoplanetary disk, the structure that receives the excess angular momentum of the collapsing cloud, is exactly the structure from which planets form. The solar system exists because the collapsing molecular cloud that formed the Sun had too much angular momentum to put all its material into a single sphere. The excess had to go somewhere, and it went into a spinning disk of gas and dust. Within that disk, over millions of years, grains of dust stuck together grew into pebbles, then boulders, then planetesimals, then protoplanets, and finally into the 8 major planets we know today. The planets are not an accident. They are not an optional feature that sometimes accompanies star formation. They are a direct and necessary consequence of the angular momentum problem. Without excess angular momentum, there would be no disk. Without a disk, there would be no planets. Without planets, there would be no Earth. The reason you exist is partly because a collapsing cloud of gas 4.5 billion years ago had slightly too much angular momentum to form a star alone. This is the mechanism. Conservation of angular momentum, acting through gravitational collapse, turns formless clouds of gas into structured, flat spinning systems. It transforms invisible residual drift into the rotation of stars, the orbits of planets, and the architecture of disks. It operates the same way at every scale where gravity compresses matter, from a pocket of gas a few light years across, collapsing into a single star to a protogalactic cloud, hundreds of thousands of light years wide, condensing into a spinning spiral galaxy. The physics does not care about scale. The conservation law applies to a collapsing stellar nursery, with the same absolute authority it applies to anything else that contracts under gravity. The rule is simple. If something shrinks, it spins faster. If it spins faster, it forms a disk. And if it forms a disk, the structures that emerge from that disk, whether planets or stars or entire galactic arms, will carry the imprint of rotation for the rest of their existence. But we have so far applied this mechanism only to the relatively gentle process of star and planet formation. What happens when gravity does not merely compress matter into a star, but crushes it into something far more extreme? When the collapsing object is not a cloud of hydrogen, but the iron core of a dying massive star, and the final product is not a star burning hydrogen in its core, but an object so dense that a teaspoon of its material would weigh 1 billion tons. When the contraction ratio is not a factor of 1,000,000 but a factor of tens of billions. The consequences of angular momentum conservation in these extreme environments go beyond anything the gentle birth of a solar system can prepare you for. What comes next takes the same simple law and pushes it into the realm of objects spinning hundreds of times per second, black holes warping spacetime around their rotation, and accretion disks hotter than the cores of stars. A massive star does not die quietly. When a star more than roughly 8 times the mass of our Sun exhausts its nuclear fuel, the core that has been supporting the entire structure against gravitational collapse suddenly loses its battle. For millions of years, nuclear fusion in the core has been pushing outward, generating radiation pressure and thermal energy that balances the relentless inward crush of gravity. The star is in equilibrium, a delicate truce between two enormous forces. Layer by layer, the star has fused lighter elements into heavier ones, hydrogen into helium, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, building an onion-like structure with the heaviest elements at the center. But when the core finishes fusing silicon into iron, the chain reaches its end. Iron is the most tightly bound nucleus in nature. Fusing iron does not release energy, it absorbs it. The instant the core fills with iron, the outward push of fusion vanishes. The truce is broken. Gravity wins. In less than a second, the core collapses. What happens next is one of the most violent events in the known universe, releasing more energy in 10 seconds than the Sun will produce in its entire 10 billion year lifetime. The core, roughly the size of Earth at the moment fusion stops, plunges inward at speeds approaching 1/4 of the speed of light. Protons and electrons are crushed together into neutrons by the overwhelming pressure. In roughly 1/10 of a second, the core compresses from a sphere thousands of kilometers across to a ball roughly 20 kilometers in diameter. The density of the resulting object exceeds the density of an atomic nucleus. A thimbleful of its material would outweigh every building in a major city. The outer layers of the star, still falling inward and unaware that the core has already halted, slam into this suddenly rigid neutron-rich sphere and rebound outward in a catastrophic shockwave. The resulting explosion, a core collapse supernova, blasts most of the star's mass into space at thousands of kilometers per second. For a few weeks, the dying star outshines its entire host galaxy. But the collapsed core remains behind, a tiny ultradense remnant that you could drive across in 15 minutes at highway speed. It is a neutron star, and it is spinning ferociously. This is where angular momentum conservation produces its most dramatic consequences. The iron core of the massive star, before collapse, was already rotating. Stars rotate throughout their lives, and the core participates in that rotation. A typical massive star's core might complete one rotation every few seconds, an unremarkable rate that would attract no special attention. But now that core has shrunk from a sphere roughly the diameter of Earth to a sphere roughly the diameter of a large city. The contraction factor is immense. Earth's radius is approximately 6,400 kilometers. A neutron star's radius is roughly 10 kilometers. That is a contraction by a factor of more than 600. Conservation of angular momentum demands that the rotation rate increase by the square of that factor. A core that was rotating once every few seconds before collapse suddenly finds itself spinning dozens of times per second. The Crab Nebula provides one of the most famous and historically rich examples. The supernova that produced it was observed by astronomers in 1054, recorded in Chinese and Japanese historical texts as a guest star so bright it was visible during the daytime for nearly a month. Nearly 1,000 years later, the expanding debris cloud still glows spectacularly in telescope images, powered by the energy pouring out of the object at its center. That object is a neutron star, and it spins roughly 30 times per second. Each rotation sweeps a beam of electromagnetic radiation across the sky, like a lighthouse lamp rotating on its mount. When that beam crosses Earth's line of sight, we detect a brief flash. The pulses arrive with metronomic precision, 30 times every second, never missing a beat. That rotation rate, roughly 3 times faster than a kitchen blender at full speed, is a direct relic of the original star's core rotation, amplified by the savage compression of gravitational collapse. Every pulse of the Crab pulsar is an echo of the angular momentum that existed in the progenitor star before it died, preserved and magnified by the conservation law through one of the most violent events in astrophysics. But 30 rotations per second is modest by neutron star standards. Some neutron stars spin far faster, reaching speeds that strain the imagination. These are called millisecond pulsars, and they achieve their extraordinary rotation rates not through collapse alone but through a second mechanism. When a neutron star exists in a binary system with a close companion star, material from the companion can overflow its gravitational boundary and stream onto the neutron star. This accreting material carries orbital angular momentum. As it spirals down onto the neutron star's surface, it transfers that angular momentum to the star, gradually spinning it up over millions of years. The process is slow but relentless. A neutron star that was born spinning at 30 rotations per second can be spun up to hundreds of rotations per second by sustained accretion from a companion. The fastest confirmed neutron star spin rate is 716 rotations per second. This pulsar, discovered in the dense globular cluster Terzan 5 using the Green Bank telescope, completes a full revolution in just 1.4 milliseconds. To put that number in perspective, in the time it takes you to blink, this neutron star has completed roughly 250 full rotations. At that rate, a point on the neutron star's equator is moving at roughly 24% of the speed of light, approximately 70,000 kilometers per second. The surface of this object travels from New York to Los Angeles and back nearly 9 times in a single second. The gravitational and structural forces required to hold the star together against the centrifugal tendency to fly apart at this speed are staggering. The matter at the equator is experiencing an outward pull that would tear apart any material known on Earth. Only the extraordinary internal pressure of degenerate neutron matter, supported by quantum mechanical effects that prevent the neutrons from being compressed any further, keeps the star intact. If it spun even slightly faster still, the material at the equator would begin to tear away, flung outward by the star's own rotation, shedding mass into space. And there appears to be a ceiling. Despite decades of searching, no neutron star has been confirmed spinning faster than 716 rotations per second. Observations suggest a speed limit near roughly 760 Hz. Theoretical models propose that gravitational wave emission from tiny asymmetries in the neutron star's shape, mountains just fractions of a millimeter tall on the surface, may radiate away angular momentum fast enough to prevent the star from being spun up beyond this threshold. The faster the star spins, the more efficiently these gravitational waves drain angular momentum, creating a natural break that caps the maximum rotation rate. Conservation of angular momentum giveth, and gravitational waves taketh away. Even the most extreme spinning object in the stellar universe is governed by the same conservation law, now battling against a relativistic drain. In 2025, NASA's NICER telescope aboard the International Space Station added a striking piece of evidence to this picture. Observations of a neutron star in an X-ray binary system revealed a spin rate that also matched 716 Hz, the same ceiling as the previous record holder, discovered through a completely different method. 2 neutron stars found using entirely different observational techniques, topping out at the same rotation rate. This coincidence strengthens the case that neutron stars have a genuine physical speed limit, a maximum spin rate imposed by the fundamental physics of ultradense matter and gravitational radiation. But neutron stars, extreme as they are, still have surfaces. They are still matter, the last configuration in which fundamental forces between particles can resist the inward crush of gravity. Cross that threshold, add enough mass to overwhelm even the quantum pressure holding neutrons apart, and matter does not find a new equilibrium. It simply loses. The collapse continues without limit, past every density, past every known state of matter, past the point where our physical theories can follow. What remains is not an object in any conventional sense. It is a black hole, and it is still spinning, because angular momentum does not care whether the matter carrying it has a surface or not. Now take the concept of extreme spin and push it past the point where matter itself can no longer resist. When a collapsing core is massive enough, roughly above 2 to 3 solar masses, not even the repulsive force between neutrons can halt the implosion. The core collapses past the neutron star stage and forms a black hole, a region of space where gravity is so overwhelming that nothing, not light, not information, not even time as we understand it, can escape. Black holes carry angular momentum, and they carry it forever. This fact might seem paradoxical. A black hole has no solid surface. It has no crust, no atmosphere, no observable internal structure rotating in any conventional sense. It is a singularity wrapped in an event horizon, a boundary from which nothing escapes. Yet it spins, and that spin is one of only 2 properties that fully define it as a physical object: mass and spin. That is all a black hole possesses. Strip away every other characteristic, every detail of the matter that fell in, every distinction between iron and hydrogen, between stellar remnant and primordial gas, and what remains is mass and spin. If the original collapsing object was rotating, the black hole inherits that angular momentum, and once trapped behind the event horizon, that angular momentum can never be radiated away through normal means. It is locked in. The physics of a spinning black hole is described by a solution to Einstein's equations of general relativity, published by the New Zealand mathematician Roy Kerr in 1963. Before Kerr's work, the only known black hole solution was the non-rotating Schwarzschild solution, which describes a perfectly spherical, motionless void in spacetime. Kerr showed that adding spin changes everything. A spinning black hole does something extraordinary to the space around it. It drags spacetime itself into rotation. Near the event horizon of a spinning black hole, space is not passive and stationary. It is moving, pulled around in the direction of the black hole's spin like water swirling around a drain, but with a crucial difference. It is not matter being dragged. It is the geometry of the universe itself being twisted into co-rotation with the black hole. This effect, called frame dragging or the Lenz-Thirring effect, becomes so intense close to a rapidly spinning black hole that there exists a region outside the event horizon called the ergosphere where no object, no matter how powerful its engines, can remain stationary relative to distant stars. Even if you pointed your spacecraft directly against the rotation and fired every thruster at maximum, space-time itself would carry you around. You would be swept along by the rotating geometry of the universe, like an ant trying to walk backward on a spinning record. Frame dragging is not a theoretical curiosity. It has been measured. NASA's Gravity Probe B satellite, in orbit around Earth, detected the frame dragging effect caused by our own planet's rotation, a tiny but measurable twisting of space-time amounting to a fraction of a degree per year. Around a black hole, the same effect is amplified by factors of billions, turning a subtle relativistic whisper into a deafening roar. The spin of black holes is measured using a dimensionless parameter that ranges from 0, representing no rotation at all, to 1, representing the theoretical maximum spin rate. At maximum spin, the event horizon itself rotates at the speed of light, and the ergosphere extends to its greatest size. Most supermassive black holes measured to date appear to spin rapidly, with dimensionless spin parameters above 0.5, suggesting that sustained accretion over billions of years has spun them up to high rates. In 2024, a team led by Ruth Daly used combined observations from NASA's Chandra X-ray Observatory and the Carl G. Jansky Very Large Array Radio Telescope to measure the spin of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. The technique, called the outflow method, relates the properties of the black hole's radio jet emission and the X-ray emission from its surrounding accretion flow to constrain the spin. The result was striking. Sagittarius A star, with a mass of roughly 4.3 million suns, is spinning with a dimensionless spin parameter of approximately 0.9, which corresponds to roughly 90% of the theoretical maximum. Its angular velocity is approximately 60% of the highest value permitted by general relativity, before the event horizon would cease to exist. It is rotating so rapidly that the spacetime around it is severely warped, distorted by the enormous rotational stresses into a geometry that the researchers described as resembling the shape of a football. This is not a slowly turning object drifting at leisure. This is a 4 million solar mass singularity, spinning at a rate that approaches the absolute limit imposed by the structure of spacetime itself. That spin is not just a passive property sitting behind the event horizon doing nothing. It is a vast reservoir of extractable energy, a spinning flywheel of warped spacetime that can power astrophysical phenomena on scales that dwarf anything else in the universe. In 1969, the physicist Roger Penrose showed through an elegant thought experiment that energy can be extracted from a spinning black hole's ergosphere. An object entering the ergosphere can split into two pieces, with one piece falling into the black hole on an orbit that effectively carries negative energy relative to an outside observer, and the other piece escaping to infinity with more energy than the original object carried in. The escaping piece has stolen rotational energy from the black hole, slowing its spin by a tiny amount while gaining kinetic energy in the exchange. This is not science fiction. It is a mathematical consequence of general relativity in the Kerr spacetime. In astrophysical settings, this principle scales up into a mechanism that may power the most energetic sustained phenomena in the observable universe. Magnetic fields threaded through the accretion disk and anchored within the ergosphere can tap the black hole's rotational energy electromagnetically, extracting angular momentum from the black hole and channeling it into relativistic jets. These jets, collimated beams of magnetized plasma launched at nearly the speed of light from the polar regions of the black hole, can extend for hundreds of thousands or even millions of light years, far beyond the boundaries of the host galaxy itself. They carry more energy per second than entire galaxies produce in starlight, and a significant fraction of that prodigious energy output may come not from the gravitational energy of infalling matter, but from the rotational energy of the black hole itself. Angular momentum, trapped behind an event horizon for billions of years, slowly converted through magnetic processes into the most powerful and far-reaching particle beams in the cosmos. Spin is not merely a property of black holes, it is their power source. Accretion disks around spinning black holes are themselves profoundly shaped by the spin of the central object. In general relativity, the innermost stable circular orbit, the closest distance at which matter can orbit the black hole without spiraling irreversibly inward past the point of no return, depends critically on the black hole's spin rate and direction. For a non-spinning black hole, this orbit sits at 3 times the radius of the event horizon. For a maximally spinning black hole, the innermost orbit moves much closer to the event horizon, almost grazing it. This difference matters enormously for energy output. Matter spiraling inward through an accretion disk releases gravitational energy as radiation. The closer the innermost orbit sits to the event horizon, the more energy is released before the material plunges in. Around a non-spinning black hole, accretion converts roughly 6% of the infalling mass into radiated energy. Around a maximally spinning black hole, that efficiency climbs to roughly 42%. For comparison, nuclear fusion, the most powerful energy source known to stellar physics, converts only about 0.7% of mass into energy. A spinning black hole's accretion disk is 60 times more efficient than the fusion process that powers every star in the universe. This extraordinary efficiency is why quasars, powered by accretion onto supermassive black holes, can outshine their host galaxies by factors of thousands. To put 42% efficiency in concrete terms, a single solar mass of material accreting onto a maximally spinning black hole would release more energy than the Sun will produce across its entire 10 billion year lifetime on the main sequence. Feeding in 10 solar masses would outperform 10 suns, each burning for 10 billion years. No other sustained natural process in the known universe comes close. Spin is the difference between a modest gravitational engine and the most luminous sustained phenomenon in the cosmos. Spin does not just shape the structure around black holes, it determines how much energy the universe can extract from infalling matter. Now scale up from individual objects to entire galaxies. A galaxy does not form the way a star does. Stars condense from relatively compact, dense cloud cores that collapse under their own gravity over timescales of a few 100,000 years. Galaxies assemble from vastly larger, more diffuse structures over timescales measured in billions of years. A protogalactic cloud might span hundreds of thousands of light years, contain the mass of hundreds of billions of suns, and take a significant fraction of the universe's age to collapse and organize into a recognizable disk or elliptical structure. The angular momentum of a galaxy cannot be explained solely by the random internal motions of its gas, the way a star's spin originates from turbulence in its parent molecular cloud. The source cloud for a galaxy is too large, the collapse too gradual, the internal turbulence too thoroughly averaged out over such enormous volumes for internal motions alone to produce the observed rotation rates. Galaxies acquire a significant portion of their spin from an entirely different source, one that is external to the forming galaxy itself: the gravitational influence of neighboring cosmic structures. Think of it this way. Imagine two people pushing a heavy table from opposite sides. If both push with exactly equal force in exactly opposite directions, the table slides without rotating. But if one pushes at even a slight angle, the imbalance creates a twist and the table begins to turn. In the cosmic web, neighboring overdense regions act as those asymmetric pushers. They do not pull on the forming galaxy from perfectly balanced directions. The mismatch between the collapsing region's shape and the surrounding gravitational pull creates a net torque that sets the protogalaxy spinning. This mechanism is called tidal torque theory, and it is one of the foundational ideas in the study of galaxy formation. First proposed by the astronomer Fred Hoyle in 1949 and developed mathematically in subsequent decades, the theory describes how the gravitational tidal field of the surrounding large-scale structure imparts angular momentum to a forming galaxy. As a region of the universe begins to collapse under its own gravity to form a protogalaxy, it is not collapsing in isolation. Neighboring overdense regions, which will eventually become neighboring galaxies and galaxy clusters, exert their own gravitational pull. This pull is not uniform, it is a tidal force, stronger on the near side of the forming galaxy and weaker on the far side. The mismatch between the shape of the collapsing protogalaxy, described by its inertia tensor, and the direction of the surrounding tidal field creates a torque. That torque spins up the protogalaxy, imparting angular momentum that the galaxy carries forward through billions of years of subsequent evolution. The direction and magnitude of the resulting spin depend on the local geometry of the cosmic web. Galaxies forming near filament spines experience different tidal fields than galaxies forming at the intersections of multiple filaments or within the walls of large voids. This environmental dependence produces a striking and now well-confirmed prediction that reveals how deeply connected galaxy spin is to the structure of the universe. Low-mass galaxies, sitting in dark matter halos with masses around 100 billion solar masses, tend to have their spin axes aligned along the filaments in which they formed. Their angular momentum was acquired primarily through smooth, steady accretion of material flowing along the filament like water through a pipe. The infalling streams carry angular momentum that reinforces the filament-aligned spin direction, building the galaxy's rotation in a coherent and predictable way. But above a critical halo mass, roughly 1 to 10 trillion solar masses, the picture changes dramatically. High-mass galaxies did not grow primarily through smooth accretion. They grew through major mergers, violent collisions between comparably sized galaxies that scramble the original spin direction entirely and reorient the angular momentum axis along a new direction. After a major merger, the resulting galaxy often ends up spinning perpendicular to the filament rather than along it. The merger effectively erases the memory of the original tidal torque and replaces it with a new spin direction determined by the geometry and orbital angular momentum of the collision itself. This mass-dependent spin transition, the flip from filament-aligned to filament-perpendicular spin, has been confirmed by both large cosmological simulations and multiple observational surveys using integral field spectroscopy to directly measure galaxy rotation axes across thousands of objects. In August of 2026, a study published in Nature Astronomy provided the most powerful observational confirmation of tidal torque theory to date. Researchers compared the angular momentum vectors of observed galaxies with predictions derived from reconstructing the primordial density field of the nearby universe. The gas component of massive central elliptical galaxies showed a striking directional correlation with the predicted primordial tidal field, detected at a significance of approximately 7 sigma. This is far beyond the threshold for a confident detection. It means the probability that the alignment occurred by random chance is less than 1 in a trillion. The angular momentum of these galaxies is not random or accidental. It is imprinted by the same primordial gravitational tidal field that sculpted the filaments, walls, and voids of the cosmic web itself. The spin direction was effectively set before the galaxy even finished forming, locked in by the geometry of the surrounding universe. This result closes a conceptual loop that stretches from the smallest collapsing gas clouds to the largest gravitationally influenced structures in the observable cosmos. Stars acquire their spin from the turbulent motions of their parent molecular clouds, amplified by gravitational collapse. Galaxies acquire their spin from the tidal forces of their cosmic environment, imprinted during the early stages of structure formation. In both cases, the angular momentum already existed in the system before the object began to take shape. Conservation of angular momentum then ensures that this initial spin is carried forward, reshaped and redistributed, but never destroyed. As the object evolves over billions of years, the mechanisms differ in detail. The core physics is identical. Angular momentum that exists before collapse persists after collapse, amplified by contraction and preserved by the fundamental symmetry of the universe. And the 2025 discovery of rotating cosmic filaments, discussed earlier, extends this story to the largest scales yet observed. If filaments, structures spanning tens of millions of light years, exhibit coherent rotational motion, then angular momentum is being generated and preserved at scales that push beyond the standard framework of tidal torque theory. Current theoretical models can explain how galaxies acquire spin from filaments, but explaining how the filaments themselves develop organized rotation requires understanding the dynamics of the cosmic web at an even deeper level. Ongoing simulations and observational surveys are working to determine whether filament rotation is common or unusual, whether it matches predictions from standard cosmological models, or whether it hints at processes we do not yet fully understand. What is already clear is that spin does not stop at the scale of galaxies. It reaches into the scaffolding of the cosmic web itself. The span of scales is almost impossible to absorb. A neutron star, 20 kilometers wide, spinning 716 times per second, its surface hurtling at a significant fraction of the speed of light. A supermassive black hole, its event horizon spanning millions of kilometers, rotating at 90% of the speed limit set by general relativity, dragging spacetime itself into a roaring vortex. A spiral galaxy, 100,000 light-years across, rotating once every few hundred million years, its spin direction imprinted by the tidal gravitational field of the cosmic web before the galaxy even finished forming. A cosmic filament, 50 million light-years long, exhibiting coordinated rotational motion detected through the careful measurement of redshifts across hundreds of member galaxies, from the crushed remnant of a dead star to the largest thread in the cosmic tapestry. The same conservation law operates across all of it. Mass that falls inward spins faster. Angular momentum, once acquired, persists unless actively transferred elsewhere. Disks form because rotation resists collapse in the equatorial plane, while allowing free fall along the poles. These are not separate explanations for separate phenomena. They are one explanation, one law, applied consistently across more than 20 orders of magnitude in physical size, from 20-kilometer neutron stars to structures spanning hundreds of millions of light-years. But this picture, powerful and encompassing as it is, has boundaries. Not everything about cosmic rotation is explained by the simple statement that collapse amplifies angular momentum. There are questions that remain open, observations that do not fit neatly into the framework, and a critical distinction between what rotates locally and what the universe does or does not do on its grandest, most fundamental scale. The conservation law tells us why things spin. It does not tell us why they spin in the particular directions they do. It does not tell us whether the universe as a whole carries any net angular momentum. And it does not explain why, in a cosmos built on a law that seems to guarantee rotation at every scale, some objects barely spin at all, while others rotate near the ragged edge of physical possibility. These unresolved questions, and the quiet but profound elegance of the answer that has carried us from clouds of gas to the largest spinning structures in the universe, await just ahead. We have followed angular momentum from clouds of cold gas drifting through interstellar space to the fastest spinning neutron stars in nature, objects so compressed that their surfaces move at a significant fraction of the speed of light. We have watched angular momentum shape protoplanetary disks into the flat nurseries where planets are born, define the elegant spiral structure of rotating galaxies, warp the very fabric of space-time around spinning black holes, and reach into the vast filaments of the cosmic web itself, where structures tens of millions of light-years long exhibit coordinated rotational motion. One law, operating with the same absolute authority across every scale, producing the same fundamental result: matter that collapses under gravity begins to spin, and that spin builds structure. The mechanism is clear. The evidence is overwhelming. But several questions remain that this mechanism alone cannot fully answer, and those questions, rather than undermining the story we have told, complete it. They reveal the true boundaries of what spin can and cannot tell us about the universe, and in doing so, they expose a deeper and more beautiful truth about why the cosmos looks the way it does. The first question is deceptively simple. If everything spins, why does everything spin in different directions? Stand on Earth and look at the solar system from above the North Pole. The planets orbit counterclockwise. The Sun rotates counterclockwise. Most major moons orbit counterclockwise. The system appears choreographed, as though someone set it turning in one direction and everything followed suit, but this coherence is local. It reflects the fact that the solar system formed from a single rotating disk whose angular momentum pointed in one specific direction. Everything born from that disk inherited the same sense of rotation. Look beyond the solar system, and the coherence vanishes. Neighbouring star systems spin in whatever direction their own parent clouds happen to rotate. There is no alignment between them. One star may rotate with its axis pointing toward the constellation Orion. Its nearest neighbour may spin with its axis pointing in the opposite direction entirely. No mechanism links one star's rotation to another, unless they formed from the same cloud at the same time. Scale up further, and the independence becomes even more apparent. Galaxies in the same cluster can rotate in completely opposite directions. The Milky Way spins one way, Andromeda spins another. Galaxies within the Virgo cluster point their spin axes in every conceivable direction. There is no master rotation, no cosmic gear system, no universal turntable that everything is bolted to. Each galaxy's spin was set by its own local tidal environment during formation. Two galaxies forming side by side in the cosmic web would acquire spin from different tidal torques, shaped by different surrounding structures, and end up rotating in unrelated directions. The conservation law guarantees that spin will exist. It says nothing about which way that spin will point. Even within single systems, spin directions can be disrupted. Major galaxy mergers can flip a galaxy's spin axis entirely, reorienting its angular momentum along a new direction determined by the orbital geometry of the collision. The mass-dependent spin transition explored earlier demonstrates this clearly. Low-mass galaxies tend to spin aligned with their host filaments because they grew through smooth, orderly accretion. High-mass galaxies spin perpendicular because violent mergers overwrote the original tidal signal. The same conservation law operates in both cases, but the outcomes are different because the formation histories are different. Spin is universal, its direction is local, and that distinction matters enormously. Within our own solar system, the exceptions encountered earlier prove precisely this point. The reverse spin of Venus, the extreme axial tilt of Uranus, and the retrograde orbit of Neptune's moon Triton all resulted from different events: ancient collisions, gravitational captures, atmospheric tidal effects operating over billions of years. Each event was unique. Each obeyed the conservation law with total precision. But none of them was dictated by a cosmic preference for one rotational direction over another. Angular momentum was conserved through every collision and every capture. The amount never changed. Only the direction did, set by the specific geometry of each violent encounter, rather than by any universal rule about which way things should turn. The universe guarantees spin. It makes no promises about which way that spin will point. This leads to the second and far more provocative question. If everything inside the universe spins, does the universe itself rotate? The idea has a long and surprisingly serious history in theoretical physics. In 1949, The mathematician Kurt Gödel, already famous for his incompleteness theorems that shook the foundations of mathematical logic, discovered a solution to Einstein's field equations of general relativity that described a rotating universe. In Gödel's model, the entire cosmos spins around an axis, and the rotation introduces bizarre consequences, including the theoretical possibility of closed time-like curves, paths through spacetime that loop back on themselves, essentially allowing travel into the past. The solution was mathematically valid within the framework of general relativity, but it described a universe very different from the one we inhabit. It contained no cosmic expansion, which immediately contradicted the well-established observation that distant galaxies are receding from us at velocities proportional to their distance. Nevertheless, Gödel's work proved that general relativity permits rotating universes as a matter of mathematical principle. The laws of physics do not forbid universal rotation. The question became empirical. Does our particular universe actually rotate? The answer, as far as current observations can determine, is no. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space with faint microwave light emitted roughly 380,000 years after the beginning of the universe, provides the most sensitive test available. This radiation has been cooling and stretching as the universe expanded, and today it arrives from every direction at a temperature of roughly 2.7 degrees above absolute zero. Its uniformity is remarkable, varying by only a few millionths of a degree from one direction to another. But within those tiny variations lie encoded the geometry, content, and dynamics of the entire observable cosmos. A rotating universe would leave a distinctive signature in this radiation. Rotation would create a preferred axis in space, breaking the isotropy that the cosmological principle assumes. It would produce a specific pattern of swirling asymmetry, a spiral-like distortion visible in both the temperature and polarization maps of the cosmic microwave background. Space telescopes, including the Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite, have mapped this radiation with extraordinary precision across the full sky, searching for exactly this kind of signal. They found nothing. The universe appears isotropic to better than 1 part in 100,000. The upper limit on any possible universal rotation is extraordinarily tight, constrained to less than 10 to the negative 9th degrees per year, over the entire age of the cosmos. For all practical and observational purposes, the universe's net angular momentum is indistinguishable from zero. This result carries a profound implication. The spin that fills the cosmos, the rotation of every planet, star, galaxy, and filament we have discussed throughout this story, is not inherited from a spinning universe. It is generated locally, at every scale, through the interplay of gravitational collapse and the conservation of angular momentum. The Big Bang did not need to spin to produce a spinning universe. It needed only to produce matter that was not perfectly still and let gravity do the rest. Local processes created local angular momentum. Conservation preserved it. Collapse amplified it. And the result is a cosmos full of spinning objects embedded within a universe that, on its largest scale, does not rotate at all. Some researchers have challenged this consensus in recent years, proposing that the distribution of galaxy spin directions across the sky is not as random as the standard model predicts. In 2025, analyses of galaxy rotation directions observed by the James Webb Space Telescope's Advanced Deep Extragalactic Survey reported a statistical excess of galaxies appearing to rotate in one preferred direction over the other when viewed. From Earth, the author proposed this as possible evidence for a cosmological scale preferred axis of rotation, potentially consistent with a rotating universe model or even a speculative scenario in which our universe formed inside a rotating black hole in a larger parent cosmos. The claim attracted significant attention but remains highly controversial within the astrophysical community. Other researchers have pointed to potential systematic biases in how galaxy spin directions are classified from two-dimensional projected images, the difficulty of establishing consistent classification criteria across different telescope surveys and galaxy morphologies, limitations in sample selection that could introduce spurious directional signals, and the challenge of distinguishing genuine cosmic anisotropy from observational artifacts rooted in the geometry of our own galaxy's dust. The mainstream consensus, strongly supported by the extremely tight constraints from the cosmic microwave background, is that these reported asymmetries do not constitute reliable evidence for universal rotation. The universe, as best we can currently measure with our most sensitive instruments, does not spin. This creates a conceptually beautiful and surprisingly profound situation. Spin is everywhere in the cosmos, but it is not fundamental to the universe's overall structure or geometry. It is emergent, an outcome of processes that operate within the universe rather than a property of the universe itself. It arises from the combination of two ingredients: imperfect initial conditions and a conservation law that refuses to let motion disappear. The universe did not start spinning. Matter within it started falling, and because that matter was never perfectly symmetrical in its arrangement or perfectly radial in its motion, collapse produced rotation as an unavoidable byproduct. Every spinning object in the cosmos is a testament not to some primordial rotation of the universe itself, but to the impossibility of perfect stillness in a physical world governed by quantum mechanics and thermodynamics. And that leads to the third open question, one that adds an important nuance to the story we have told so far. Why do some objects barely spin at all? If angular momentum is conserved and collapse amplifies rotation, you might expect everything in the universe to spin rapidly. But reality is more nuanced than a single rule applied uniformly. Some objects rotate slowly, and their slow rotation is not evidence against the conservation law. It is evidence that the conservation law operates with more subtlety than the simple statement suggests. Angular momentum is conserved, but it can be transferred from one form to another, from one object to another, from one mechanism to another. A slowly spinning object has not lost its angular momentum. It has given it away. Tidal locking, explored earlier with the Moon, provides the clearest example. The Moon appears to barely rotate, turning just once per month, but that appearance is misleading. Its angular momentum has not disappeared. It has been relocated. Over billions of years, Earth's gravity raised tidal bulges on the lunar surface, and while the Moon was still spinning faster than its orbital period, those bulges sat slightly ahead of the line connecting the two worlds. The offset created a gravitational torque that steadily drained angular momentum from the Moon's spin and fed it into the orbit. The total angular momentum of the system never changed by a single unit. Only its distribution shifted from rapid spin into a wider, slower orbit. The Moon still carries enormous angular momentum. It is simply banked in orbital motion rather than visible surface rotation. This redistribution operates wherever tidal forces reach. Close-in exoplanets orbiting red dwarf stars within potentially habitable zones are widely expected to be tidally locked, permanently showing one scorching face to their star, while the other hemisphere faces perpetual frozen darkness. Compact binary star systems gradually synchronize through the same mechanism. In every case, angular momentum has not vanished from the system. It has been methodically redistributed through gravitational interactions, flowing from the spin column into the orbital column of the angular momentum ledger. The conservation law is satisfied with perfect precision. The object simply ended up in a state where its visible rotation is slow or synchronized rather than rapid and conspicuous. Some stars rotate extraordinarily slowly for different reasons. Magnetic braking, the same process that allows stars to form without spinning apart, continues operating throughout a star's life. As a star ages, its stellar wind, a stream of charged particles flowing outward from the surface, is channeled along magnetic field lines. The wind carries angular momentum away from the star, gradually slowing its rotation over billions of years. Young stars spin rapidly, old stars spin slowly. Our own sun, roughly 4.5 billion years old, has been magnetically braked from a youthful rotation period of a few days down to its current 25-day rotation period. Given enough time, magnetic braking can reduce a star's rotation to a crawl, but the angular momentum is not destroyed. It has been carried away by the stellar wind, dispersed into the interstellar medium, where it joins the vast reservoir of angular momentum floating through the galaxy. Even black holes are not exempt from the possibility of slow rotation. Not every black hole approaches the theoretical speed limit the way Sagittarius A star does. Some supermassive black holes have been measured with surprisingly modest spin parameters, well below half the maximum value. These sluggish spinners likely grew through a series of chaotic, randomly oriented mergers rather than through sustained accretion from a consistent direction. When two black holes of comparable mass merge from random angles, their angular momenta partially cancel. The resulting black hole inherits a spin that reflects the messy, partially cancelling sum of its parent's contributions rather than the coherent buildup that prolonged accretion provides. Orderly feeding from a stable disk builds fast rotation. Chaotic merging from random directions can leave a supermassive black hole spinning surprisingly slowly. Gravitational wave radiation provides yet another channel for angular momentum loss, one that connects the story of cosmic spin to the newest frontier of observational astrophysics. Rapidly spinning neutron stars with tiny structural asymmetries, mountains on their surface perhaps only fractions of a millimeter tall, radiate gravitational waves that carry angular momentum away from the star, gradually slowing its spin over millions of years. Binary star systems, spiraling inward toward merger, radiate enormous quantities of angular momentum through gravitational waves, the ripples in spacetime, predicted by Einstein, and finally detected directly in 2015 by the LIGO Observatory. The gravitational waves observed from merging black holes and neutron stars are, in a very real and physically precise sense, angular momentum being released into the fabric of spacetime itself, radiating outward at the speed of light in expanding shells of warped geometry. The conservation law still holds with absolute precision. The angular momentum is not destroyed, it is radiated away, encoded in ripples of spacetime that carry the information of the merger across the universe. Every slowly spinning object in the universe tells the same story. Its angular momentum was not absent. It was transferred, redistributed, exported, or stored in a form other than visible rotation. The conservation law does not guarantee that every individual object spins fast. It guarantees only that the total angular momentum of any closed system remains exactly constant over time. How that angular momentum is distributed among the components of the system, whether in rapid spin, slow orbit, outflowing wind, or gravitational radiation, depends on the physics of each individual situation. The law sets the total. The details determine how it is shared. And now we arrive at the deepest layer of this story, the question beneath all the other questions. Why is there angular momentum in the first place? Why was the universe never perfectly still? The answer reaches down to the very foundations of physical reality, to the place where physics meets philosophy and both arrive at the same conclusion. In a universe governed by quantum mechanics, perfect stillness is not just unlikely, it is forbidden by the most fundamental principles of the theory. The Heisenberg uncertainty principle, one of the cornerstones of quantum mechanics, states that you cannot simultaneously know the exact position and exact momentum of any particle with arbitrary precision. The more precisely you determine one, the less precisely you can know the other. If a particle were perfectly stationary, its momentum would be exactly zero, known with infinite precision, but this would require its position to be completely uncertain, spread out across all of space. For a particle confined to a finite region, like a cloud of gas, perfect stillness is simply not allowed. Every particle always carries some minimum amount of motion, a tiny irreducible quantum of jitter that can never be eliminated, not even at absolute zero temperature, not even in principle. This quantum indeterminacy has cosmological consequences that echo across the entire history of the universe. The matter that emerged from the Big Bang was not arranged in perfect symmetry. Quantum fluctuations during the epoch of cosmic inflation, the briefest fraction of a second at the very dawn of cosmic history, created tiny variations in the density and velocity of matter throughout the infant universe. Inflation stretched these quantum fluctuations from subatomic scales to cosmic scales, seeding the universe with imperfections that would eventually grow into galaxies, clusters, and the cosmic web. These fluctuations were minuscule, variations of roughly 1 part in 100,000, barely detectable even with the most sensitive instruments ever built. But they were real, and they were everywhere. They guaranteed that no region of the universe was perfectly uniform in density, and no cloud of matter was ever perfectly radial in its motion. Every patch of the primordial cosmos carried some tiny, random, residual velocity that was not purely aimed at a center. Every patch, therefore, carried angular momentum from the very beginning. When gravity eventually caused these patches to collapse, forming the first stars, the first galaxies, the first large-scale structures, the angular momentum was already there, written into the initial conditions by quantum mechanics itself. Conservation took over from there, amplifying the quantum whisper into a cosmic roar. The rotation of every planet, every star, every galaxy, every accretion disk in the universe today traces back, through an unbroken chain of conservation, to fluctuations that occurred in the first tiny fraction of a second after the Big Bang. The universe spins because quantum mechanics made it impossible for the universe to be perfectly still, and gravity amplified every imperfection it found. This is the strange reason. Not a force, not an engine, not a cosmic hand setting things in motion. The strange reason everything spins is that the universe was born imperfect, and physics will not let imperfections be forgotten. Angular momentum is the cosmos's memory. It records the initial conditions of every collapsing cloud, every forming galaxy, every merging pair of black holes, preserving information about events that occurred billions of years before any observer existed to witness them. A spiral galaxy rotating once every few 100 million years is remembering the tiny tidal torque that nudged its parent cloud into rotation when the universe was a fraction of its current age. A neutron star spinning 716 times per second is remembering the rotation of a stellar core that existed before the supernova blew the rest of the star into space. Its furious spin, a compressed echo of a motion that began in a gentle molecular cloud millions of years before the star was even born. Sagittarius A star, spinning at 90% of the maximum permitted by general relativity, is remembering every accretion event, every galaxy merger, every infalling stream of gas that added angular momentum to its growing mass over the course of billions of years of cosmic history. None of these objects chose to spin. None of them were designed to spin. They spin because the physics of conservation and collapse left them no other option. The information encoded in their rotation has been passed down, transformed, amplified, but never erased, through an unbroken chain that stretches all the way back to the quantum fluctuations of the newborn universe. The pattern that emerges, when you step back and look at the entire picture, is not one of cosmic mystery. It is one of physical inevitability. Given a universe where quantum mechanics forbids perfect symmetry, where gravity causes matter to collapse, and where angular momentum is conserved with absolute precision, rotation is not a surprising outcome. It is the only possible outcome. Disks will form, planets will orbit, stars will spin, galaxies will rotate, black holes will drag spacetime into co-rotation. Cosmic filaments will exhibit coordinated angular momentum across tens of millions of light years. All of this follows, with mathematical certainty, from three ingredients: imperfect initial conditions, gravitational attraction, and a conservation law connected to the rotational symmetry of space. The universe did not need to be wound up. It did not need an external push. It did not need a prime mover or a first rotation. It needed only to exist with the properties it has, to contain matter that is not perfectly arranged, and to operate under laws that conserve what is already present. Everything else, every spinning disk, an orbiting moon and rotating galaxy, is a consequence. There is a particular kind of beauty in this, not the beauty of design, where someone arranged everything with purpose and intention. This is the beauty of inevitability, the realization that the universe could not have turned out any other way given the laws it obeys. The spinning of planets is not imposed from outside. It grows from within, cultivated by the same gravity that holds everything together, preserved by the same symmetry that makes the laws of physics identical in every direction. The cosmos does not spin because something made it spin. It spins because spinning is what matter does when it falls inward, and cannot forget the way it was moving before the fall began. Look up at the night sky one more time. Every point of light you see is rotating. The stars are turning on their axes, some slowly, some so fast their equators bulge outward against the centrifugal strain. The planets around those stars are orbiting in thin, flat planes, each one carrying angular momentum imprinted by the disk from which it formed. Each orbit a preserved memory of a spinning cloud that existed before the planet was born. The Milky Way beneath your feet is rotating, carrying the Sun and its entire family of planets along at 500,000 miles per hour on a 230 million year journey around the galactic center, a journey it has completed roughly 20 times since it formed, and will complete many more times before the last of its stars go dark. Somewhere beyond what your eyes can see, neutron stars are spinning hundreds of times per second, their surfaces moving at a significant fraction of the speed of light, held together against impossible centrifugal forces by the pressure of degenerate matter. Black holes are dragging spacetime itself into whirlpools of warped geometry, their rotation powering jets that outshine galaxies, and filaments of the cosmic web are turning with a slow, coordinated grace that was only discovered in our own generation, extending the story of cosmic spin to scales that the earliest astronomers could not have imagined. All of it traces back to the same quiet rule. Angular momentum, once present, is conserved. Collapse amplifies it. Disks are the inevitable geometry of rotating matter falling inward, and the universe was never, not for a single instant, since the first quantum fluctuation stirred the primordial void, perfectly still. The strange reason everything spins is not strange at all. Once you understand it, it is the most natural thing in the universe. A tiny amount of motion, born from quantum uncertainty in the first fraction of a second of cosmic history, trapped by gravity, preserved by the deepest symmetry of physical space, and amplified across 14 billion years of cosmic evolution into the planets, stars, galaxies, and black holes that fill the night sky. The universe does not spin because of some dramatic cosmic event or some mysterious external force. It spins because spinning is what happens when imperfect matter collapses under gravity, the only force that operates across every distance and every scale. Gravity finds the motion that was always there. Conservation refuses to let it disappear. Collapse concentrates it into something visible, structural, powerful. And the result is everything you see when you look up at the sky on a dark, clear night. And it starts right where you are standing. The rotation you feel every morning when the sun rises over the horizon, that turning of the earth that gives you day and night and has done so for 4.5 billion years, is the same phenomenon. It is governed by the same law, connected to the same unbroken chain of conservation that stretches all the way back to the birth of the cosmos. The Earth spins because the cloud of gas from which the solar system formed carried a tiny surplus of angular momentum that could not be erased. That surplus was amplified by collapse, stored in the spinning disk that became the planets, and inherited by every world that condensed within it. You are riding on a piece of that original rotation right now, at over 1,000 miles per hour, just as you were when this story began. The cosmos is not stillness interrupted by occasional rotation. It is rotation all the way down, from the quantum jitter of the first particles to the slow turning of the largest structures ever observed, connected by a single unbroken thread of conserved angular momentum stretching across every scale the universe contains. And the law that holds this thread together, that connects the spin of an electron to the rotation of a cosmic filament, has been the same since the first instant of time. It will remain the same long after the last star burns out, long after the last black hole evaporates into the silence of deep time, long after the last photon stretches beyond detection in the expanding dark. Angular momentum is conserved. The universe remembers every motion it has ever made, and that memory, written in the quantum imperfections of the beginning, and amplified by gravity across the entire history of the cosmos, is the reason everything spins.